So good morning, everyone. Welcome to this NMIS Insights online webinar on the circular economy for manufacturers. Today, you've got three speakers. So the first is me, I'm Alex Cochrane. I'm an R&D engineer at the Lightweight Manufacturing Centre, which is part of NMIS, and I've got a background in composites for aerospace. Andreas is our remanufacturing lead at NMIS, and Jill is our sustainability lead at NMIS. Just some housekeeping points for you to take note of. This is recorded, this webinar is recorded and will be made available on our YouTube channel. Everybody will have their webcam and microphone switched off, other than us. You can type questions. We would encourage you to ask questions in the chat tool, which I think Laura's highlighted there. And we do have quite a bit of time. We've got 20 minutes at the end for Q&A to answer those questions. So we would encourage you to ask questions during the webinar. So NMIS, just to give a bit of background, is an industry-led research centre which represents £65 million of investment from the government, University of Strathclyde and the Scottish Enterprise, and which basically aims to form a bridge between industry and academia and act as a hub for problem solving, productivity and skills. So if you imagine it as a hub, basically for knowledge exchange and expertise, as well as networking, with a very strong manufacturing capability so that it can basically act as an industrial laboratory. As I said, NMIS represents a joint venture between some of the parties that are shown here, so it's very much a national effort. So NMIS is composed of two primary specialist centres: the Advanced Forming Research Centre, specialising in advanced metalworking, and the Lightweight Manufacturing Centre, specialising in advanced composites and lightweighting, with both centres having a renewed focus on sustainability. As I've said, two of our speakers today, Jill and I, are from the LMC, while Andreas is from the AFRC, but we're all working under the NMIS umbrella. There's other elements to NMIS, so infrastructure in the form of the Manufacturing Skills Academy, the Digital Factory and the Collaboration Hub, and these help to form basically the backbone for that manufacturing hub that the NMIS was. So the AFRC has been completed in 2011, and that's in Shannon, and the LMC is currently at Westway Park in Renfrew. We're in a sort of temporary location at the moment, and we'll all move to the NMIS Digital Factory, which is due to be completed by the end of next year. So today, I'm going to be giving you an outline of some innovative work we're doing on sustainable and modular manufacturing. Andreas will be talking about working with metallic materials in the context of the circular economy. And Jill will be talking about where we're currently at with composites recycling and our plans for that. I'll talk very briefly first, with 15 minutes for Jill and Andreas after me, and then we'll follow that up with a Q&A session. So again, please do ask questions in the chat during this webinar. So today I'm going to be taking you through very briefly an innovative catapult project that we're running and that I'm leading, which is on low cost, low impact and modular manufacturing for the future and for the circular economy. So at the moment in Scotland, the backdrop to manufacturing is two major themes. The first is the aim to get to carbon net zero by 2045, which is a very ambitious target set by the Scottish Government. And the second is the fact that the industrial economy is made up mostly of SMEs and not of majority OEMs and prime contractors. So the image on the right shows a plot of composites manufacturing facilities, which is very kindly taken from Composites UK, and that's from 2019. And it gives an idea of the sparsity of just the manufacturing activity we have in Scotland compared to the rest of the UK. So NMIS is aiming to invest in commission projects that deal with both of these things for a sustainable and linked up supply chain. That's kind of context of why we're doing this project. But the kind of more refined context is in pilot production lines. So a pilot production line is basically a small scale production line for de-risking and developing production processes prior to moving to full scale processes. Most of you will be familiar with the TRL scale, so I've shown that at the top. Basically, that's the technology readiness level scale, and it represents the readiness of the technology being developed for the market. And where pilot lines come in is between TRL 4 to 6, where you're trying to prove out your manufacturing technology. Generally, they're in this format in the center here. Material goes in, several operations are performed on that material, and then you get your part out at the end. So if you take that in a composites context, these overall process flows can look wildly dissimilar. And this means that you basically will need a lot of different capabilities to prove out that product before you go to production. For that reason, and that doesn't only apply to composites, basically pilot lines are very capital and energy intensive to set up. Generally, they're very bespoke and they're geared towards proving out processes for a single product generally, or very similar products. So if you've got differing products in your product line, or you're an SME, different SMEs working across different sectors and making different products, you probably need to invest heavily to set one of these up. So we think a good concept for the future is the reconfigurable pilot line, or RPL. So this takes the fixed capability of a traditional pilot line and instead makes each cell a reconfigurable one, which is what the image on the right shows here. So each of these reconfigurable cells would have changeable capability rather than fixed capability. So we think this has distinct advantages. The system's modular. The idea is that you can drop cells in and out of your line or grid, as we've shown, as needed. So changing capability requirements or changing demand. You can remove cells just as easily if you don't need them. We think it's more sustainable in the sense that you're expending a lot less energy and effort in setting up or decommissioning your line, and it involves a lot less commitment in terms of factory space or fixed footprint. We think that it's a low risk offering for SMEs. So we want to explore ways to basically not push the capital costs of this onto SMEs that want to make use of it. So just to expand on those gray boxes, those reconfigurable cells, this is an example of what one of those might look like and is what our first cell will look like without manufacturing capability installed. So there's 4 key elements to this. The first is our smart platform, which is this gray platform you can see here. So that's actually made up of machined metallic plates, which stack together a little bit like Lego. We're currently working on a new design of this, which goes together even easier than this one. The idea is that this is designed with the user in mind. It's very rapid to install and uninstall, can be done in a single shift, and it's reconfigurable that you can change the capability that you install on it. In this particular configuration, we've got a large industrial robot, so that will have an end effector on it to perform our first manufacturing capability, which is AFP, automated fibre placement. And then we've got supporting robotic elements, which are basically there to replace humans. So cobots perform material handling and machine vision, and our AMR, which is an autonomous mobile robot, will provide material transport capability around the workshop. So I'm going to finish now, but just very briefly before I do, we've actually made a full-scale plywood mock-up of this, of our smart platform with the supporting robotic elements, and that's in our workshop at the LMC currently. So this is images of that here, and this is our first cobot being installed and commissioned on that. And this is our AMR transporting material in the workshop. So you can see this is the kind of genesis of this reconfigurable cell. It's very early days, but we are starting to make this. And we actually do have our aluminium prototype under construction at the moment as well. So that's being assembled in our workshop. Basically, we aim to have this sort of configuration in our workshop in the next 6 months or so. And many of these items you see are in procurement currently. So you can see there, that's the beginnings of a reconfigurable line. So that's all from me. I'm actually going to pass over to my colleague Jill, who's sorry, I'm going to pass over to Andreas, who's going to talk about metallic materials in the circular economy.
Thank you, Alex, for the very interesting presentation. Let me quickly share it on my screen. Yeah. Second. Okay. So I hope you can see my screen. Yeah, perfect. So as Alex already introduced me, I'm Andreas Reimer. I'm leading the remake team in NMIS, and I will talk a little bit about enabling remake for a circular economy in manufacturing. So obviously we have very big challenges towards net zero, especially with the government target now, the net zero about 2050. Scottish government has even more ambitious targets about 2030. So, and what we found is that 55% of actually all the greenhouse emissions are caused by, or can be reduced by energy storage, more renewable energy and so on. However, 45% still remaining in manufacturing. So, and this 45% we are trying to tackle with a circular economy approach, especially around remake. So I'm talking about circular economy. I need to roll back a little bit and explain what we are currently. And currently, obviously, we are in a linear waste system. So basically, we have a production from virgin materials to manufacturing, usage, and then it goes into landfill. So it's a linear system. So using it and then throwing it away. However, the circular economy system, as the name already suggests, basically manufactures it, and then it has a circle, so to reuse, remanufacture, repurpose components back to its original state or even better. So this obviously comes with a lot of challenges. So so first of all, we need to adapt processes for it. We need to develop the processes. We need to understand what kind of so we need to understand how the component will perform later on, and also we need to reassure companies that the component will perform as it should, as it did before. So, however, we also run some studies which actually showed that that applying remake reduces significantly the greenhouse emissions in applying the circular economy model. Right. So in the remake testbed, so basically how we call the remake scheme here in NMIS, we're looking at the entire remanufacturing value stream or remakes value stream. And this starts really from the cleaning and inspection section. So basically a component would come in used, obviously. So we would need to look at the component, clean it. So that's also a very critical part of the remake process to clean the components, because often they are kind of somehow contaminated, and then doing some kind of inspection, also internal inspection, how is maybe the component fatigued inside, what's going inside on. So, and then once we have gathered all those information, we then being able to rebuild, recondition the component using especially AM. In NMIS currently we have the capability on laser metal deposition with powder, warm wire arc additive manufacturing, cold spray, and we are also working with melt, which is a friction stir additive manufacturing process. And after depositing some material back onto the component, so it needs to be machined again to its final size, where we're obviously looking into machining, heat treatments, and so on, because obviously it needs to get back to spec. And then after all those processes have been done, we then look into, okay, did we actually meet the criteria it actually needs? We check it again with NDE, automated ultrasonic, and so on, CMM, to really check geometries and what's going inside. And as part of obviously being an RTO, that's going a step further than maybe industry would on a regular basis. We're looking into, okay, residual stresses, how's the residual stress in the component performing, the material testing, how, and also the material characterization, because in some applications this one is also a very important part. Obviously throughout, we're also quite active there. So because we need to look into, okay, what is the life cycle analysis? We need to understand how much carbon we actually save, how much we actually produce during the remanufacturing process. Validation, certification, very important as well. Simulation will help us to optimize and really predict the remanufacturing processes. Education is a very key point as well, because a lot of a lot of processes and people need to be educated around remanufacturing, what it is, how it can actually benefit, and obviously the design for remanufacturing. So basically designing components before they're actually being manufactured the first time to be remanufactured later on in life. So that's a very much a key point in the remake. So I would like to give a couple of practical examples around remake and what we did here at NMIS. So one is the digital project, which we just now, I think 2 years ago, we had a forging die, which forged bucketies. So those kind of bucketies, obviously, they are under very high shock loads, pressure, thermal loads, and they have also a very high level of wear. So here in the top right picture, you can see a worn die. Yeah. So and we run remanufacture. So we build a process around it with digitalization, so on. So scanning, as I just explained those points, and optimizing the process, and used LMD to deposit a layer back on, machine it back to the original basically size. So you can see the process, but I give you on the side also some figures. So the original die, basically as it is here, was able to do 1,300 components. So after we remanufactured it with a hard-facing alloy, because we knew, okay, those areas are really kind of worn out, so they can't use them anymore. So we can use a hard-facing alloy, which makes it even longer. So, and they put it back into their service, and it was then for another 1,400 components in service. So we extended the die life by 108%. So from 1,300 components, we went to 2,700 with the very same die. That's obviously not only has impact on the CO2 emission saving, but also obviously on cost, lead time, and so on. So here a quick overview on the process. So you can see here, this is the laser head. So it's a, as I said, laser metal deposition. It's blown powder with the laser. So the laser comes in the middle and powder is around it, which is kind of channeled into the middle with the focal point. And in the focal point, the metal melts and it lays down a layer. So that's obviously, it does it a couple of times. So you can build up layer by layer to actually build up some small features. And this particular component has been done in our hybrid machine. So that's why you can see the very same setup. You can deposit and actually machine. That's actually not very common. Usually you have either AM or machining in a machine, but this machine can do both. Okay, another project which is currently running, we call it Hybrid DED. It's a ATI funded project where we want to combine, or we combine forging and forming with a DED process, in particular WARM, to add features or to remanufacture features on large aerospace components. Obviously looking throughout at heat treatment, NDT, busy testing and machining. And you can see this project has also a very big consortium, so it has a lot of traction and interest across the board. The next, sorry, too quick. So the next one was actually a demonstrator we did, I think 2019 in in the FRC as part of the machining day, open machining day. So basically, this one is to remanufacture a gear teeth. So the idea is basically one single teeth or multiple teeth are worn out or broken, sheared off, whatever the case is. And the idea is now that we machine down the broken teeth and use, for example, again, the LMD system again to build up a new teeth and machine it then to size to put it back into service. So this one obviously was just a demonstrator, so the gear was never in service or later on, but it just was demonstrating the capability of those kind of technologies, so that basically we can instead of throwing the entire gear, because the gear obviously can't be used anymore if one piece is sheared off, throwing the entire gear, which obviously has a lot of carbon emissions. We just remanufacture a single teeth, which is a fraction of the emissions and costs. Yeah, so you can see here on the left-hand side, the partners we were involved in this demonstrator. So we did it with hybrid manufacturing technology, HMT, OpenMind, Mitsubishi, and Vericut. We created this demonstrator. So this one, in this case, was a case-hardened, forged gear steel. And here's some of the parameters we use. So 800 watts. You see, so the depositioning time and the machining time, that's just a fraction of what you would need to actually manufacture a complete gear. So you see, so we deposit the entire teeth in just 9 minutes and then machine it in another 6. So so it's a very quick repair method. So, and especially for companies to bring components back into service for any other components, remanufacturing can be a very good and very quick turnaround here. Okay, so yeah, in conclusion, basically, so we use novel AM methods to utilize really prolong the life cycle of metallic components. We can, as you can see, significantly reduce the CO2 emissions and waste streams in for metallic components. Also, we can reduce the amount of components in the warehouse. So because we maybe don't have to stock up as much anymore, because we know we can achieve shorter lead times to remanufacture. And then also the we need to really kind of develop a broader acceptance for it. And yeah, so and also obviously, as we have shown in the digital project, those remanufactured components can really withstand in very extreme conditions. So where we have shock loads, thermal loads, and so on. So it's not just okay, just for the look or for superficial kind of repair or remanufacture, but it can be even applied into very extreme conditions. Okay, so I think that's basically it. Thank you very much for listening. I think now I'll pass over to Jill.
Hello, just share my screen. Can everyone see my screen now?
Yeah, Joe.
Thank you. So hello everyone, my name is Jill. Sorry, just full screen. So my name is Jill. I'm the sustainability lead of the Lightweight Manufacturing Center. And today I will talk about our testbed project, the Sustainable Composites, and which is also one of the key elements for our micro circular economic development in our center. So First of all, I would like to give you some brief understanding about the challenges we're facing for composite industrial. So hopefully from the graph here, you can understanding like the market size and the demand for composite material keeps increasing. It is not just a benefit to the aerospace and automotive sectors, and also works with the marine, like renewables, and also of course construction sectors. So with this increasing demand, we do need to think about the end-of-life solutions for composite material. And it has been identified as the top things we need to consider from lots of like industrial facing workshops and the summit. So for example, like 100% recycled and recyclable composite parts was voted top priority in Composites UK and Composites Leadership Forum's vision for sustainable composites in 2019, and also in the very successful HVMC cross-category project Rediscover, the recycling and the reuse composite material has been identified as the most urgent of 13 priorities. And also we keep receiving pressures from the legislation. So in the near future, we don't have an option called landfilling. So hopefully this gives you a brief ideas about why we're gonna do that and why it is so important. It is not just from crazy academic ideas. It's based on the full industrial requirement. So next step, I will lead you to some more detailed numbers about our current issues and the status of recycling and reuse. So probably you can't imagine like there's 62,000 tons per year end-of-life carbon fiber waste to be generated. And if we only talk about aerospace sectors, there's an estimated value of 23 tons per year of end-of-life carbon fiber composite waste will be generated and of course unrecycled by 2035. And there's graph telling us about the waste volume from the wind turbine blade. So you can see around 2030, we're gonna face sharp increasing volume of waste generated from the wind farm. It's just talking about like the first few generations of wind turbines facing their retirement. So it is really urgent. We need to find out the solutions to deal with this and give them a suitable plan. So what is the current status for end-of-life solutions? So landfilling is still the main rules. You can say there's 35% of carbon fiber and 67% of glass fiber still delivered to the landfilling. And there's only 20% of carbon fiber, 13% of glass fiber being properly recycled. But recycled doesn't mean properly reused. So within that, you can see there's only 2% of carbon fiber and 60% of glass fiber actually being properly reused. So hope this number is telling us like how urgent it is. And after show you some challenges and issues, I would like to give you our plans and the vision for our next step. So this is the vision for our testbed program called Sustainable Composites. So initially, we will collaborate with academics and the other RTOs to gathering all the innovative ideas and technologies. And at our center, we will do a bit of tailoring and scaling up. After we're confident with all the products and process we're gonna deliver, we will do a knowledge exchange to cooperate with our industrial partners, and also all the technical data here will benefit the government bodies to do the legislation decision and do a bit of analysis about our environmental and the economical impact. So here's at least some key areas we will focus on for our program. So of course, initially we will develop a pilot scale recycling and reuse production lines. And after that, we will of course refresh and update our sustainable composites design and manufacturing methodologies. After coupling with the digital twin, we will be able to provide design of customized sustainable composite manufacturing system. And after setting up everything here, we will be able to use the data to generate some assessment and a report for life cycle and cost modeling. Of course, all the data will be very useful and collected to supporting the this legislation making, and also help the government to make another sustainable development from the angle of society and the environment and the economy. So that's the high-level vision of our program. And here I will show you a more detailed flowchart about our development of closed-loop sustainable composite manufacturing lines. So the first step, we will collect the waste from OEMs and also all of the composites user, and do a bit of waste stream tracking and analyzing. After that, we will review and identify the most suitable recycling technologies for each waste stream. And after that, we will collect the recycled fibers and convert that to more high value and useful recycled fiber intermediate products. And after after updating the design and manufacturing methodologies, we will also passing the certification, and finally hand over this sustainable composite product to our industrial partners. So this program will focus on all the elements listed here, and I think the top important thing is the recycling technologies. So that's next step. I will do a brief introduction about different recycling technologies. So for our research program, we will more focus on the material reclaim category rather than the lab filling. So all of the most advanced recycling technologies are included in the thermal, or somewhere you can say they call it thermal plus chemical process. So the first thing I will talk about is called pyrolysis. Pyrolysis has already been commercially used and generated the first generation recycled carbon fiber products. And then the second one is called the food asphalt process, which has been developed by the University of Nottingham for carbon fiber recycling, and also our colleagues from Advanced Composites Group at University of Strathclyde use this process doing glass fiber recycling. It can provide very high production rates and a much cleaner fiber compared to the product you can get from the pyrolysis process. And the final one is called solvensis. So for solvensis is still at the lab scale stage. Lots of researchers still focusing on the process optimization, reduce the energy cost and increasing the production rate. So at the right-hand side, I did some simple graph and figures to show you some comparison between producing the virgin carbon fiber and the recycling routes. So you can see the top one is telling you the embedded energy cost for producing the virgin carbon fiber, and also lots of different recycling technologies. You can easily get the conclusions like recycling technology will cost much lower energy compared to producing the virgin carbon fiber. And also the bottom one is telling you the CO2 emissions for the traditional carbon fiber manufacturing lines and the recycling lines. So you can say we're not just focusing on the mechanical performance to optimizing our recycling technologies. We also collaborate with researchers from different areas to looking at and analyzing, assessing these technologies from different angles. So that's basically the introduction about the recycling technologies. So after recycling, you can collect the fibers like this. Looks like a fully random and a 3D fluffy. So it is completely different format compared to the virgin carbon fiber materials. So we need to get some support from some process we call that reprocessing manufacturing lines to convert that recyclates to more useful and high value products. So we can easily do that with traditional mechanical recycling to melt that to powder or manufacture that to pellets. Of course, the market size for this kind of material is large, but it has already been fully filled. And so the companies developed some product like non-woven and 3D preform has already been used in the commercial manufacturing. But the problem is the mechanical performance for this kind of material is not that very high. So again, like researchers also considering this challenge and provide some solutions. For example, the hybrid, yes, you can coupling the recycled carbon fiber with some thermoplastic fiber filaments. So you create some yarns which can use in textile industry. So, and also the allied tools which developed by the University of Bristol. So you can use that with the 3D printing and also automated fiber placement. And in the end, like there's some products called Align Tape, which developed by the University of Nottingham. This material is mainly focusing on the high value and high volume production lines. So that's the current solutions and the current products we can find. So what we're gonna do in our center, we will occupy two different production lines. One is called the non-woven production lines. We will convert the recycled fibers and combine with some other nature fibers and the sustainable fibers, and also recycle the thermoplastic fibers to generate like fiber reinforced intermediate materials, and then provide that to develop a prototyping product with our industrial partners. And then the second line is called is basically getting some ideas from the traditional textile industry. We will tailoring that process to make it more suitable to produce recycled fiber materials. And also you can use that to do some further like composite manufacturing. So these two lines here is try to cover like different fiberless range, because for composite recycling, it's all about size reductions. So we just need to make sure we can provide a full solution and full story to our industrial partners. So that's our capability development. So next step, I will show you a simple case study developed by our partners from the ACG at University Strathclyde. Basically, it's an example for recycling and reuse the glass fiber composites from wind turbines. So the first step is you take a scrap from the waste wind turbine blade, and then you do the first and the second step of size reductions and put that into the full aspect recycling technologies. And after that, ACG got their chemical treatment technologies, which can allow 80% recovery of the mechanical performance of the regenerated glass fiber. And after that, you can convert the regenerated fiber to make a small scale like wind turbines, and finally bring that to the wind farm to become a new wind turbine blade, generate sustainable energy. So hope you enjoy this small story about our current development. So after that, I will show you a summary about our micro-circular economy story. So there's another two projects, as one is called RPL, as mentioned by Alex before. So the other one is called Future Fiber, which is also focused on generating sustainable material, but also more focused on the raw material side. So we will replace the traditional resource to manufacturing more sustainable carbon fibers, and coupling with recyclates to fit that into more advanced automated manufacturing lines, and developing the product to fit into our industrial sectors, and then generated this circular economy story. So that's all about our sustainable composites project. Hope you enjoy this example and case study. So that's the next step we're gonna do is with all the technologies and the material, we're gonna refresh and updating our composite material supply chain. So we will bring new technologies to the waste management, and to get them being able to deal with the composite material. And also we will reactive some traditional industrial, like this textile and chemical industry, so get them to be able to manufacturing more advanced sustainable composites. As I mentioned before, it can be non-woven or multifunctional composite material. And also we will collaborate with some like design companies and also across the manufacturing companies, do the prototyping, and finally hand over our sustainable composite product to our end user. So that's how we benefit the whole supply chain. Hope you enjoy this. So then I will hand over to Alex to chair the Q&A section. Thank you.
Thanks very much, Jill. That was really interesting. If you could just hold your slide there, that'd be good. So I have a question here. I think it's probably for Andreas, which is how much carbon emissions can you actually save by utilizing the remake processes?
Yeah, thank you, Alex. Yeah, so basically the remake process, as I said, is you know, as a circular method scene. So it depends really on how we calculate those kind of emissions. So if, let's say, for example, we manufacture one component, it has an X amount of emissions embodied in the component. So if this one gets thrown away, so obviously we have this, let's say, this 100 kilo of emissions is thrown away. Yeah, so basically it's gone. So, however, if we kind of remanufacture it, so we basically saving this 100 kilo, or almost, you know, more than 100 kilo, because we just kind of maybe put some emissions, maybe 1 or 2 kilos into the component, and then saving basically the other 100. So with just 2 kilograms, we can save 100. So that's why those kind of calculations, and if you do it not just once, but 2, 3, 4 times, so as long as the component is still being able to be remanufactured, so you can actually get easily into the thousands of percent of saving emissions.
Okay, thank you, Andreas. That was a very good answer. I have another here that is regarding my slides, the RPL. So is the platform size fixed or can it be changed? So I'm going to assume that is about the in-plane size of the, you know, because I talked about the height being able to be changed, but in terms of the size of the platform being 2 meters by 2 meters, I'm not sure if I showed that on my slide, but it's 2 by 2 meters. We picked that as a very kind of sweet spot for manufacturers making things across different sectors, that generally you can fit a lot on 2 by 2 meters, but you can either join 2 by 2 meter platforms together to make a bigger platform than that, so 4 by 4 meter or 2 by 4 or anything like that. But we're actually working on another design which uses a 1 by 1 meter sort of smaller unit that repeats. So instead of being across instead of having one big 2 by 2, you've actually got multiple 1 by 1s, and really you can build that as large as you want. And that's now in the advanced stages of design. So as I've said, we're prototyping the aluminium 2 by 2 platform in our workshop currently, but we're actually pretty close to be able to prototype this new version, which is basically built up of smaller building blocks, and the actual platform itself goes together a lot more like Lego. So it's very customizable and very easy to change it to be of the right size that you want to be. But we do get that question a lot, especially from either smaller companies who are interested in something smaller, maybe less heavy duty, or larger companies who are interested in making very large structures. You know, are we constrained by the size? And I would say that we're not. We just need to work with people to ensure we give them the right system for the size of component they're making. Jill, this one's probably for you. What sort of timescales are there for your development work that you showed? Because I think you showed your intentions over the coming years, but what sort of timescales are on that?
Yeah, so the basically the capability development, so all the production lines we fully installed and able to running in the end of next year, so in our new building. And also at the same time, we also keep doing a CR&D development with our partners. So we already submitted some bid applications so with our industrial and academics partner. So that's basically our current timelines for the next year. And after we installed our production lines, we will keep doing research work, developing new materials, and coupling with different recycling technologies to convert that to material being able to fit into different level of market. It can be aerospace or automotives. It's based on the production rate and the value of the end products. So that's basically roughly the timelines for our development.
Okay, thanks very much, Jill. There's possibly one more that's suitable for you, which is what's your main area of focus for composites recycling? So out of all those things you showed, what's the key thing you're focusing on?
So for our program, it's you probably understand we are the member of the Catapult Center, so we more doing medium TRL level things. We're not doing mainly focus on the fundamental research. So we would like to do scaling up the technologies. So what I can say is there's already been so many good recycling technologies there in the research market. So what we're gonna evaluate and understand the different technologies, and the case in here is be able to create the links between each steps, from the recycling to reuse and to redesign and then remanufacturing. So get those rigs be able to talk to each other and get the industrial partner more understanding the methodologies to use of this material. So our focusing is more a link everything together and be able to telling a full package of stories from the recycling to reuse. So that's our focusing things. Thank you.
Okay, thanks very much. Thanks very much, Jill. Last couple of questions, I think. Another one for you, Andreas, is how can NMIS support us to enable remanufacture in our company? What avenues are there for getting the support for remaking?
So I think it's as I showed in one of my slides. So we're supporting really from right from the beginning of maybe designing, but right to the process development up into almost the implementation of the process. So, and I think the easiest way, obviously, to get in contact with us is just it's not just for myself, but obviously also for Alex and Jill. Just note down our email addresses and feel free just to drop us an email. And even if you're not sure if we are the right person, so I'm sure we can certainly direct you in the direction for the right person for whatever matter. If you want to manufacture, remanufacture, recycle, whatever it is, we certainly can point you in the right direction and help you. Also, if you feel okay, maybe we want to go down an avenue on a C&D, so a funded project by the government. So also feel free to contact us, and we can certainly support you on that journey. So because that's not always the easiest, especially for SMEs. It usually requires a lot of effort, and we certainly have the know-how and capability to support you very much on that journey as well.
Okay, thanks, Andreas. Just like to invite our attendees, just if anyone has any further questions, please feel free to ask us. Jill has put them in the chat just now, or Jill has put up on this slide, all of our email addresses are there. Please do take note of these and direct questions to us via email if you do have any questions about any of our projects. But if there's no further questions, I'm going to draw this webinar to a close. Thank you everyone for coming. I will pass over to Laura, who's going to do some give some final remarks before we end the webinar.
Thanks very much, Alex, and thank you so much to our speakers today, Jill, Alex, and Andreas. And a survey will follow shortly by email. We'd be most grateful if you could take that. It's 2 minutes of your time. And please do join us for future webinars. We've got another one next week with our Manufacturing Skills Academy, and we'd love to see you there. I'm just going to close the webinar now. Thanks very much, everyone. Bye.
Bye-bye.
Thank you.